broadcasting. So Ying, please take it away. It's all you now.
Great, thank you, Sasha. So, welcome to the Cinema Community Science Seminars. Today we have two excellent speakers, Jun Liang from University of Calgary and Xiaojia Zhang from University of Texas at Dallas. So Jun is going to talk about aurora continuous structures, observations.
Give me a second. So I can't hear. It's just me or
Oh, thank you. I think I mute myself sometime. Yeah, so let me start from the beginning. Welcome to the Community Science Seminar. Today we have two excellent speakers, Jun Liang, a research scientist from University of Calgary, and Xiaojia, associate professor from University of Texas at Dallas. So Jun will talk about aurora continuous structures, observations, and modeling. And Xiaojia will talk about exploring outer radiation by electron losses, a low altitude perspective from ALPHIN and ISS. Before we dive into the science talk, let me remind you, we saved the questions towards the end of the seminar. And also, as Sasha mentioned, that our community science seminar series now have a website. So at the website, you can see the recordings of previous seminars, and you can also watch the YouTube live stream or join the Zoom seminar from the website. And we also have a link from which you can receive email notifications and updates about our seminars. And both the links for the email subscription as well as the website seminar website can be found in the chat. Without further ado, let's start our first presentation. Jun, please take over.
Can you guys see my screen?
Yes.
Yes.
Okay, so
it's not in the presenters. Okay, it is now.
Okay, yeah, this should be now. So yeah, this is Jun Liang from the University of Calgary. First, thanks for the invitation. Today, I'm going to talk about the aurora continuum structure. First, I would like to thank my colleagues in our aurora imaging group, particularly the Emma Spansbeek and Josh Houghton, who actually contributed a lot to this talk. And also want to express my gratitude to a lot of the other the worldwide colleagues. And well, just a spoiler here, that this cover photo actually represents one of the aurora continuum events I will be a bit focused on today. So this is the outline of my talk today. I will give a sort of the brief historical review of the optical continuum structure, how it was caught our attention, it caught our attention and was realized by the space science community. And I will then introduce some of our recent observations of the aurora continuum, and I will talk about the preliminary modeling efforts and the model data comparison. And finally, I will summarize and offer my own perspective of this research direction. So, well, a background continuum has long been known to exist in the dark sky, but that's very weak and it's certainly invisible. So in terms of the visible optical structure that consists of the continuum spectrum, I think Steve is the first that stroked the space science community. So this plot is from the Megan's famous paper, which is the first report of the Steve spectrum based on the T-Rex spectrograph measurements. So we confirmed that the major source of the Steve luminosity comes from the overall enhancement of the. So can you see the mouse here? So comes from the overall enhancement of the continuous spectrum over the background. So this is what we call the continuum. The result was confirmed later, the study led by myself. I included another set of the instrument that is the OXO, namely the Athabasca Geospace Observatory. OXO has two non-aurora wavelength channels at 480. Okay, so it's a little bit blocked by the channel. So it's at 480 and at 620. And they are designed as the background channels for the H beta and the 630 aurora emissions. And normally, this background channel represents the ambient white light and it contains very weak the aurora signals, probably due to spectral leakage. However, in the case of Steve, these background channels show up the Steve structures as well. So, and 2 years later, moderate the geostorm occurred during the Canada Thanksgiving Day. So this is the video captured by my friend Chris Vaslav, who is a kind of citizen scientist in Calgary and the leader of the Alberta Aurora Chaser group. So yeah, so okay, you can see the curve structure develop appears suddenly and then moves very fast. So, well, okay, actually, Chris and I met in the bar, and Chris showed me this video and asked me whether we have the kind of a scientific image or observations. The first thing I checked was actually the oxo, and it immediately struck me that this is not something traditional auroras. So here I plot side by side the H-beta proton emissions line and the 480 background channel. So this is the 486 H-beta 9. It shows the main proton aurora band, the band which doesn't have any kind of counterparts in the 480 background channel. But later, when the curve structure develops, as one can see, the curve structure show up on the proton aurora H-beta channel and the background channel as well. So basically, we have something kind of morphologically quite different, but spectrally similar, something similar to Steve. So we sampled the spectrum of this curve structure and its surrounding the high latitude and the low latitude labors and compared the spectrum and the plot here. So the blue curve here denotes the curve structure, and the black and the green curves here denotes its ambient higher and latitude and lower latitude labor. So not surprisingly, there's some kind of a prominent aurora nice bands. I marked some here. But our key interest here, there's a systematic rise of the spectrum intensity over broad wavelength range of this curve structure. So here's the movie from our T-Rex RGB camera. So yeah, so the blue line here indicates the scan line of the meridian spectrograph. So I just want to bring your attention to the rapid eastward motion. Yeah, I will play it again. And just bring your attention to the rapid eastward motion of this curve structure. And on the left side, I presented the evogram that's from the RGB. And the horizontal axis here is the time, and the vertical axis here is the longitude. So the slant trees here indicates the eastward propagation. Its velocity around 5 kilometers per second. So, well, there may be some other possible explanation of such a motion, but to me, it's very likely to be associated with the fast plasma flows. So, yeah, and we know that such fast flows naturally imply intense plasma heating. So, yeah, after that, we have performed kind of the systematic survey using our T-Rex RGB and the spectrograph data, and established the presence of such aurora continuum structures. The paper in this regard was led by Emma and published on Nature Communication the last year. So, well, the structures may look kind of so I'm trying to play the movie and seeing the structures may look kind of the white or the kind of the gray or whitish in RGB observations because of the presence of the substantial continuum the component. This can be confirmed from the spectrograph measurement. So let me play the movie. So I just can stop here. Can you see this kind of the gray toned structure on top of the green line aurora as well? Can you see that?
Yeah.
Okay, so let's move on. Later there are some other, yeah, okay. Can you guys see the white, kind of the whitish structure on the left, on the west side of the green line aurora as well?
Yes.
So yeah, this is this. I will comment on the picture because yeah, you can see that this kind of a whitish continuum structure is located on the west side edge of the green auroras, and yeah, I will comment on this picture later in this talk. So okay, so yep, no, sorry. Here I show the superimposed optical spectrum of the continuum emission structures. So yeah, I'm not gonna into many kind of technical details. You may find all these details in the paper. Just to quickly mention that, yeah, those continuum emission structures are always found to be embedded or kind of immediately adjacent to bright auroras. And based on the subtract spectrum, it means that meaning that the continuum spectra subtract it label the aurora spectrum, and the continuum emission itself typically has a strength about 10 to 30 really per nanometer. So this is the strength of the continuum, the structure. And in terms of the spatial scale, the aurora continuum have a kind of the spatial scale, typically around a few tens of kilometers up to several hundred the kilometers, but without any favored shape. That I mean, it can be of any kind of the irregular shape of the sort of the structure. So yeah, this results was published, and now I'm going to mention some of the work in progress led by our students, Josh Houghton. The first is the superposed epoch analysis on the KP context. So yeah, time 0 here indicates that observe the start time of the aurora continuum. So as you can see, the aurora continuum has a strong tendency to occur at the maximum KP epochs. And actually, if you look into details, it acts as a kind of the threshold of the KP around 4. We don't see this occurs at KP values lower than KP than 4. So this is definitely the kind of a phenomenon limited to extended the intervals of the geomagnetic the activity times. So yeah, okay. So one may question that the KP has a kind of low resolution of 3 hours. So in this regard, we also examine the HP30 index, which has 30 minutes resolution, and found that the general pattern remains unchanged at all. And yeah, I think that when Emma first reported this in the last AGO4 meeting, and one comment here was that the KP dependence might probably be a low latitude effect, because the Lucky Lake station is normally at the subaurora latitude, and it requires higher KP for the aurora to reach the Lucky Lake station. So, well, in this regard, we also performed the analysis only for the Rabbit Lake station. So this is only for the Rabbit Lake station. And so, well, Rabbit Lake station is always in the aurora over, so there's not subjected to this low latitude effect. And again, you see kind of the result basically remains the same. So the superposed epoch analysis is on the DST context, and we can see that the aurora continuum happens almost exclusively during storm intervals, and tend to occur during the main phase around the minimum DST the epoch of a storm. So in my opinion, the result implies that the storm time precondition of the upper ionosphere and the thermosphere before the aurora continuum formation is quite likely. And well, it's actually probably needed, as I shall mention later in this talk. So we're also trying to do the statistics of the energy flux and the mean energy associated with the continuum structures, aided by the T-Rex aurora transport model inversion. And well, this is not an easy task for a number of reasons, and it's still in progress to date. So on the left side, I just give a kind of example. The upper 3 panels show the T-Rex RGB images with the continuum structure marked, and the lower panels shows the total precipitation flux map inferred from the T-Rex state and the ATM immersion. Well, I just want to quickly mention that the preliminary analysis indicate that this sort of the aurora continuum structures are typically accompanied by total precipitation flux of few tens of the erg per the square centimeter per second. So yeah, that's all about observations. And now I'm going to turn to the theory and the modeling effort for the aurora continuum structure. And well, this is certainly not some kind of traditional aurora emissions we are familiar with. And to date, the most proposed mechanism for such a continuum is the so-called NO2 continuum, produced in the reaction between the nitric oxide and the oxygen. So, well, obviously, the nitric oxide density is the key here. And the nitric oxide is produced in the thermosphere through various chemical reactions. Well, actually, I'm keeping adding them according to the colleagues' suggestions. And However, if you carefully check, this conventional way of producing the nitric oxide may not be able to produce the required density to cause the NO2 continuum of typical steep brightness. So Brian, Brian Harding, actually proposed another potential mechanism. So in that, the nitrogen molecules could be excited to the high vibrational levels by collision with fast drifting ions. And if the vibration level is larger than 11, they have the sufficient energy to overcome the energy barrier and in this reaction and produce nitric oxide and in turn the NO2 continuum. So, however, the feasibility of the Brian's proposal for Steve was challenged by my study published last year. So, well, basically, so in this paper, we performed the quantum calculations and derived the rate coefficients for the vibrational translation excitation led by the fast ions, and applied these coefficients in the context of the side and the Steve. And our conclusion is that the vibrational translation, the excitation led by side ions is unable to produce sufficient NO2 continuum to explain the steep brightness. There are two main reasons for such a failure. The first is the low ambient nitrogen density at the steep altitudes, and the other is the depleted plasma density in the side region. Both the VT excitation led by the fast ions and the excitation led by thermal electrons are proportional to the plasma density, but the density is largely depleted in both the E and F region ionosphere within the side channel. So as we now know that well by the satellite and the model from both observations models. Well, however, again, the failure to explain the Steve with this sort of the continuum doesn't necessarily mean a failure to explain the aurora continuum. The aurora continuum is a different story because first, aurora continuum occurs in the E region where the neutral density is much stronger. Secondly, we have strong aurora precipitations here and expect to have a much enhanced electron density instead of the depleted density. And thirdly, the aurora electron precipitation itself can contribute to the vibrational excitation of nitrogens. So yeah, for that purpose, we also need the rate coefficients of the nitrogen vibrational excitations led by electron impact. And this is done in another work led by myself. And so I'm not gonna into kind of the many details. Just quickly mention that we got new cross sections and rate coefficients for the electron impact, excitation, de-excitation, and the nitrogen vibrational module in the T-Rex ATM essentially is kind of entirely redesigned with this new data sets and with time-dependent, self-consistent coupling among the aurora electrons, ionosphere electrons, and the nitrogen vibrational distributions. So yes, now we have all the tools to study the phenomena. So our goal is to model the time-dependent evolution of the vibrational excitation of the nitrogen molecules and the nitric oxide productions, and see whether it can produce the nitric oxide, the NO2 continuum comparable to the observations. So yeah, that's just just a mention of one run here. So in this run, I impose a kind of 5 kilometer per second flows and Maximilian electron precipitation with 50 erg per square centimeter per second total flux and the 4 keV characteristic energy. So this precipitation parameters from the T-Rex measurements, which I will mention later. So this here I present the electron ion temperature that provides from the simulation 10 minutes after that I imposed the strong flow and aurora precipitation. And as you can see, there are very strong enhancement of the electron and ion temperature. Yeah, I particularly point out the existence of the anomalous electron heating here. So under such a kind of strong electron ion heating, so well, of course, we may expect that the neutral temperature will increase substantially. But unfortunately, currently, there's no neutral module in my model. So I can't calculate the neutral temperature response in a safe, consistent way. So in the following model, so the simulation, so that I just simply assume the ad hoc increase of the 30% over the MCSE, the empirical model for the neutral temperature. So, okay, so let's play the moving for the temporal variation with the vibrational, the distribution of the nitrogens. The horizontal axis here is the vibrational level, and the vertical axis here is the altitude. So as I can see, so yeah, I think I need to play it from the beginning. So there's kind of the excitation quickly extends to high vibrational levels at around kind of 110 kilometers in less than 1 minute, and then becomes kind of sort of the quasi steady afterwards. Such high level of vibrational excited nitrogen becomes the dominant source of the nitric oxide production. And we confirm that the nitric oxide density can reach comes to a high level up to several 10 to the power of 9 per cubic centimeter due to the high vibration of excited nitrogens and the strong and the flow and the aurora conditions. So yeah. Okay. So basically, so this is the kind of the result we are most most interesting. So I'm going to show the comparison of our optical outcome of our model run with the T-Rex observations. So the green line, the model is 76 kilorelli and the T-Rex report is 80 kilorelli. And for the blue line, the model gives 12 really, and the T-Rex observation gives 12 really. So I have to clarify here. This is not some kind of the magic coincidence. The agreement is simply because we purposefully choose the precipitation parameters to match the green line and the blue line observations. So, okay, so the meaningful thing is that the bottom panel, which shows the model, the NO2, the continuum intensity, which that kind of in our model reaches about 12 really per nanometer. And in the observations, the T-Rex observation, as I said, is about 30 really per nanometer. So, well, I think it's reasonable to say that our simulation achieved the kind of the sort of the order of magnitude agreement with the observed intensity of our continuum structures. But well, of course there are some kind of challenges and issues. One of the key issues is the major uncertainty is the neutral atmosphere, as I mentioned. I don't have a kind of neutral self-consistent neutral atmosphere module. And for example, if I just give an ad hoc the increase of the 30% over the empirical, the model temperature, the neutral temperature here, if instead I give a 50% of the increase of the neutral temperature, I got a kind of the continuum, the intensity of reach about, I think it's 15 really per nanometer instead. So yeah, this is sort of the kind of the little bit sensitive to this kind of choosing of this sort of the neutral profile. And the other issues, the rise time of the continuum intensity is a bit longer. It takes about a couple of minutes for this kind of rise. Well, if you think this should be okay, so you miss one thing. So in this story, because yeah, so basically we assume kind of the fast flow structure, and we assume the precipitation moves with the fast flows. But the neutrals can't follow. The neutrals is slow. The neutrals can't. There's no. So if you think about the scenario of a kind of intensification of the immobile, the neutrals against the moving aurora structures, which I gave a kind of the cartoon here. So this the green the band indicates the precipitations, and the pink dots here indicates the neutrals, and the size of the dots indicates the intensification. And you can see that actually, so the level of the intensification of the neutrals depends on the time it stays in the precipitation structure. So that means that the neutral intensification is kept by the scale and the velocity of the structure. So the strongest intensification comes with the scenario that it comes from the upfront edge of the precipitating structure and exceeds the trailing edge of the precipitating structure. So that gives another deduction that the strongest neutral intensification tends to occur at the trailing edge of the aurora structure, which, well, okay, so as I said, it's indeed, sometimes we see this indeed case. We see this sort of the continuum structure on the kind of the edge of the green auroras. But still, we still have the kind of the cap effect. So think about it. We have a 5 km/s of the moving structure, and if you assume this structure has a kind of, for example, 20 kilometers spatial scales, and it only takes 40 minutes for this to travel through. So, and we see that, and in our model, the rise up time for the NO2 continuum is typically a couple of minutes. So this is kind of still remains to be an issue in our the current simulation. So, well, okay, so how to proceed? So I think it's reasonable to say that from the model, the simulation result, that the NO2 continuum appears to be the one plausible candidate mechanism of the aurora continuous structures. However, to make it kind of quantitatively closer to the observations, some sort of the pre-enhancement of the neutrals and the self-consistent neutral variations seem to be kind of needed. So yeah, just quickly mention some of the key components I'm considering I'm testing so far. That include the nitrogen density and oxygen density. Well, this is NO2 continuum, so it definitely relies on the nitrogen and oxygen densities. And also the atomic nitrogen density, this will kind of play a role in the accelerate the rise up time of the continuum. And of course, the neutral temperature, as I mentioned. So I played with the parameters and I have a kind of a feeling that some sort of a condition to make this a kind of some of this kind of parameters increased by a factor of up to 2 may be needed for the model to have a kind of the better agreement with the actual observations of the continuum structure. So I'm not sure it's kind of achievable or not, but it's clear that we need kind of the incorporation of a model into a kind of sort of the global ionosphere thermosphere models in future. So basically, this is the end of my talk. I just give a summary here. So we introduced recent observations and some key features of the aurora continuum structures. And within the framework of the T-Rex ATM, we develop a model to simulate the production of the nitric oxide and the NO2 continuum under strong flow and aurora conditions in an attempt to explain the observed aurora continuum structures. And the preliminary model outcome is in order of magnitude agreement with the observations, suggesting that the NO2 continuum might be one plausible candidate mechanism of the aurora continuum structure. But the challenges remain. And the coupling to the global the IT models that include the preconditioning and the self-consistent variation of the neutral atmosphere is required for the modeling effort to proceed. Yeah, thanks. So that's.
Thank you so much for the talk. As said, let's save the questions towards the end. So let's move on to Xiaojia Jiang.
Okay, should I share the screen now? This one. Can you see the presentation now?
Yes.
Is it in full screen mode?
Yes.
I'm not sure. Okay, thank you. Yeah, because I have two screens. Okay, good afternoon, everyone. This is Xiaojia Jiang from UT Dallas. And today it's my pleasure to talk about our recent work on radiation belt electron losses using the low altitude datasets from ALPHN and International Space Station. So first, I would like to acknowledge all my co-authors listed here, and also to the rest of the ALPHN, Carnage, and Maxi team for providing data used in this study. So a brief introduction about the precipitation. So as we all know, that this precipitation from the magnetosphere usually occurs in two regions in Earth's magnetosphere. The first one is the plasma sheet, or the magnetotail region. The second is the outer radiation belt region. In the plasma sheet precipitation, there are two main populations of electrons that can be precipitated. The first one is mostly related to those aurora population that June was talking about in the lower energy range, in the lower energy end. And the other one is the energetic population, mostly scattered or precipitated by magnetic field line curvature scattering in the magnetotail. And in the radiation belt, there are also two populations of electrons there that can be precipitated. The first one is those injected from the plasma sheet that has energy of tens to hundreds of keV. And these electrons are predominantly scattered by Western mode wave scattering. And the other population is more about relativistic electrons with energies approaching greater than 500 keV, approaching a couple MeV in the radiation belt. And they are mostly scattered by the emic waves there. So these populations of precipitation actually connects our magnetosphere to the ionosphere, as June was talking about, to all these chemical reactions and also the heating of the ionosphere. But in this study, we'll be not focusing on those auroral electron precipitation, but more on the energetic part of the precipitation. So that in energy perspective, we'll be focusing about the precipitation with energies above tens of keV to a few MeV. So from this altitudinal profile of total ionization rate as a response of monoenergetic electron beams at different energies, we can see those energetic electron precipitation can enhance or influence the ionization rate at a lower altitude compared to those auroral electrons, which mainly occurs at below tens of keV here. And in addition, so they have been shown this relativistic electron precipitation in particular can penetrate to this lower mesosphere or even upper stratosphere to cause or contribute to the ozone depletion via a series of chemical reactions. So that's why this energetic particle precipitation has received a lot of attention in recent years. But in order to study them, we need to measure them first of all. So that's why, you know, where to or how to measure them. That usually that we want to resolve the loss cone so that you can directly capture those electrons that fall within the loss cone that will be precipitated into the ionosphere within 1 Bounce period, right? So that's why from this illustration, we can see along the magnetic field line, the loss cone size actually widens as we progressively move to higher latitudes. So that's why usually we place the spacecraft in low altitudes in order to resolve this loss cone and also resolve the precipitating particles. And shown on the right-hand side is one example of pitch angle measurements or pitch angle spectra measured at low altitude. So from this, we can see that at this altitude, we can directly discern those loss cone particles or those particles that will be precipitated versus those particles that are locally trapped along this bounce trajectory. So that's why that's how usually that we will be measuring this particle precipitation. And one of the recent missions that was capable of doing this precipitation measurements was UCLA's Alphen CubeSat. So just to quickly remind you, Alphen has these two identical 3U CubeSats orbiting around the Earth in LEO orbit and also in polar and near circular orbit, actually. So that's why it can quickly traverse a range of L shells and different regions of the magnetosphere very fast. And was in orbit for 4 years from 2018 to 2022. And the main advantage of this data set is that because the energetic particle detector is spinning with the CubeSat, so that's why it was able to capture a full pitch angle spectra during each of the half spin or during each of the 1.5 second time interval. And this pitch angle spectra was measured for energy range of 50 keV to about 5 MeV. So that's exactly the energy range we'll be talking about in this study. Then how does the data look like here in the Alphen dataset? So here shows 2 example orbits from Alphen on the downside and on the dusk side respectively. So that as we talk about, one great advantage of Alphen dataset is that it can capture the full pitch angle range, right? So that is all the particles that from 0 pitch angle to about 180 pitch angle with respect to the background magnetic field will be captured by the energetic particle detector in this CubeSat. So that's why in their routine measurements, we can directly plot this energy spectra of those locally trapped particles or those particles with perpendicular pitch angles, and those energy spectra of precipitating electrons or those electrons with pitch angle within the loss cone. And also we can use the ratio of these 2 fluxes or this precipitating versus trapped flux ratio, which is shown in the 3rd panel here, to really signify the intensity of precipitation along the Alphen track. after excluding those, the variations of the trapped electron fluxes due to the fast traversal of different L shells of this CubeSat. So using these routine measurements, Alphen was able to capture a range of precipitation patterns in different regions of our magnetosphere, from the plasma sheet to the outer radiation belt, or even to the inner radiation belt, which is not shown here, unfortunately. And the focus of this study, we will be mainly talking about just 3 primary precipitation patterns that can happen in the outer radiation belt. As marked in this illustration here, the first one will be those Westermode wave-driven precipitation, predominantly occurring on the downside. And the second one will be the image wave-driven precipitation, mostly occurring on the dusk side. And the last type will be those field line curvature scattering-driven precipitation, mostly restricted around the midnight sector. So then how does the Alphen data look like for each of the precipitation pattern? What kind of signature shall we expect? So here shows a couple of examples for each of these 3 precipitation patterns. The first of all is the first 2 examples are for the waste wave-driven precipitation. So we can see that along these 2 trajectories of Alphen, if we were to look at the precipitating to trapped flux ratio, we see this very bursty precipitation with strong intensity of precipitation that also has this decreased intensity with increasing energy. So this is exactly the signature of wave-driven precipitation, as seen both in these 2 orbits here. And except for this kind of case studies to discern the signatures related to Westermode wave-driven precipitation, that we can also use the statistics of this data set to derive the typical energy spectra related to the wave-driven scattering. So this has been listed here for your reference. Or in terms of energy, we can see that most of the wave-driven precipitation are restricted to below 1 MeV, but at times that probably you can also already see here that at times of this specific burst of precipitation, the energy range can be extended very close to 1 MeV actually, due to the specific properties of the Westermode waves, most likely. And the second type of example we show here is for the image-driven precipitation. So on the left is 1 orbit of image-driven precipitation measured by Alphen. So again, that if we were to look at this bursty precipitation with very strong precipitation intensity, we can see that this precipitation are rather localized in energy, mostly at around these relativistic energies, close to 1 MeV. And of course, in this event, it was extended to sub-MeV energies to about 200 keV in this case, and most likely related to those non-resonant scattering effect from the emit waves, or just resonant scattering of the high frequency spectra or in the high density region. This is still up in the air actually. And on the right-hand side, it shows a recent study using those low altitude measurements to directly look at the distribution of this image-driven precipitation with respect to MLT and L shell. So we can see here that most of this precipitation occurs on the dusk sector, as expected for image waves. And the last type, which is the main focus of this study, will be the field line curvature-driven scattering or driven precipitation. So here shows again 2 examples, one for ions, one for electrons, and the other is for ions in this plot here. So one signature of this field line curvature scattering driven precipitation is this dispersive signature in the energy versus latitude or versus time domain, so that you can see that this when we move towards the lower L shell, which is on the right-hand side in this left-hand event, so that we progressively encounter this isotropic fluctuation or those precipitation driven by the curvature scattering at higher and higher energies as a result of the magnetic field topology there. So that's why we can use this dispersive signature to identify the inner boundary of this field line curvature scattering region, or in other words, that this reddish region are all this plasma sheet region that we expect to see in the equatorial magnetosphere. And this IB, or this isotropic boundary, marks the inner edge of this plasma sheet region, and forward from this dispersive signature will be encountering the plasma sheet, both for the electrons and ions, where those curvature scattering is expected to operate almost all the time. So of course, in this study, we'll be focusing on the curvature scattering of electrons only. And also more recently, I would like to point to you one of these recent studies using the Alphen data has shown that this curvature scattering precipitation has been able to extend it has been able to scatter relativistic energy electrons when they penetrate to inner magnetosphere, or specifically to the outer radiation belt, as you can already see in this event on the left-hand side. So this is exactly the focus of this study here, so that we will try to answer, how often does this curvature scattering will be able to scatter those relativistic electrons in the outer radiation belt, or in other words, how often, how important this curvature scattering mechanism is to the radiation belt dynamics. In order to do so, or in order to address these two questions, we will need an extensive data set with almost continuous observations of the precipitation in the outer radiation belt. So that's why we chose to use this precipitation measurements from the ISS, from the International Space Station, and specifically that we use these two instruments called MAXI and CARLET, mounted to this Japanese module of the ISS. Why do we choose it? So first of all, that as we all know, that ISS is moving in another low altitude orbit with low inclination. So this low inclination just makes it to map to very limited L shell range, which primarily correspond to the outer radiation belt region. So that's why we will be able to have a very clean data set that is restricted to the outer radiation belt, so that we can look at how often this field line curvature scattering happens there without being possibly interfered by those curvature scattering events in a higher L shell in the plasma sheet. And that's one point. And the other point is that this CARLET and MAXI, over the past decade, they have accumulated a quite appreciable amount of data sets for us to do this kind of statistics. And of course, that from the name of these two instruments, you can sort of speculate that they are not originally designed for the magnetospheric particle measurements, but rather for this astrophysical particles or astrophysical measurements in our galaxy. But in this study, we'll be using those more or less what they call these background measurements to measure those magnetospheric particles. Specifically for CARLET, there are two energetic particle detectors that can actually detect electrons in two integral energy channels, about greater than 1.6 MeV and greater than 3.6 MeV, respectively, for these two channels. And for MAXI, they will be using this radiation belt monitor that measures greater than 300 keV electrons by two sensors, two identical sensors mounted at different directions with respect to the magnetic field. Approximately, we can think this horizontal channel to be perpendicular to the magnetic field line, and this that zenith channel or Z channel to be roughly sampling these precipitating particles, very similar to the POST data set actually. So that's the two data sets we'll be using to specifically look at how often or how important curvature scattering can be in the radiation belt dynamics. So in order to do this, remember that this correlate or maxi doesn't have this fine energy resolution as alpha has. So that's why we need to compare with the alpha recognized signature or precipitation patterns to see or to pick up the appropriate criteria for us to be able to identify each of these three precipitation patterns in the ISS dataset. So here shows two such conjunction events between ISS and alpha during the intervals of wave-driven precipitation. So all the following plots will be organized in a very similar way. So that the top two panels are those measurements from alpha, followed by the count rates by counts actually from maxi and correlate. The last panel are just multi of the ISS and alpha, just to show how close these two spacecraft are with respect to each other. And all these quantities are plotted against this magnetic latitude in order to basically compare them against each other. So from this, we can see that this alpha was able to capture this bursty precipitation during the first event on the left, and very roughly corresponding to the same, almost the same magnetic latitude. Maxi also captured this in this precipitating channel or Z channel, capture this localized peaks in this greater than 300 keV channel, so which is very consistent with the weak precipitation that we see at alpha. And similarly, on the right-hand side, the alpha this time captured this very intense precipitation, as you can see by this reddish precipitating to trapped flux ratio. And in the same time, that RBM or maxi was also capturing this very intense flux of precipitating electrons in contrast or relative to this trapped flux, which is shown in red here. And sometimes you can see that even this burst here can trigger a similar or simultaneous burst in this maxi X channel, indicating that this MEV electron precipitation can happen simultaneously or can be driven simultaneously by the Whistler waves. So that's why, based on this kind of conjunction event, we'll be using this localized peaks in the maxi data to identify those precipitation patterns potentially related to Whistler mode wave scattering. And in order to separate them or distinguish them from image wave-driven precipitation, which can also trigger the similar local peaks in these two energy ranges, will be requiring for this data set that it doesn't have local peak in the correlate Y channel, which is at multi-MEV channel, in order to separate them from image waves. And similarly, that we have looked at this conjunction event between ISS and alpha for image-driven precipitation. So similarly, that during this orbit, we see this localized precipitation at greater than 1 MeV, most like predominantly in the energy range, and almost at the same magnetic latitude that this correlate at ISS capture this simultaneous burst of precipitation in both X and Y channel, indicating that this is a rather extended precipitation from 1 MeV to a couple MeV, very consistent with what Alphen showed here. And on the right-hand side, again, this will be the bursty precipitation that we think that is potentially related to image wave scattering. And during this event, different from the left-hand side one, we can see that the precipitation was extended to below 1 MeV at alpha. And interestingly, similarly, at the maxi and correlate data, that we see this simultaneous with the correlate X channel peaks here, that this maxi data also show very strong precipitation in this black trace here, indicating that this most likely corresponding to the same extended or expanded precipitation that Alphen was observing. So that's why we'll be using this localized peaks in the correlate data to identify those image-driven precipitation from the ISS dataset. The last type will be those curvature scattering-driven precipitation. So that shown here are the two examples from, again, two conjunction examples between alpha and ISS. So very clearly that this dispersive signatures at alpha will be those so-called isotropic boundary for electrons. These two are both for electrons. And almost simultaneously, or by this I just mean that at the same magnetic latitude, we see that this MAXI data actually shows a very sharp transition from this isotropic fluxes which is indicated by this almost overlapping flux between these two channels of these isotropic fluxes to the anisotropic fluxes, indicating that this is likely the inner boundary of this curvature scattering driven precipitation, or in other words, this is likely the isotropic boundary for electrons along each of this trajectory here. And very interesting that I just wanted to point out to you here that at the inner edge of this IB, correlate also shows a strong peak in the X channel, indicating that this potentially is those high energy electron precipitation at lower latitudes, as alpha was capturing here at the inner edge of this IB. And this relativistic electron precipitation simultaneous with IB or curvature-driven scattering is not necessarily happening in every of this IB capture at the ISS. Say for this event on the right-hand side, this localized X channel peak is kind of far away from the IB actually. So that's why we think that in this event is most likely related to this, yeah, sorry, I forgot these animations. It's most likely related to those localized image-driven precipitation in this conjunction event. So that's why in this ISS dataset, we'll be using this transition region from the isotropic flux to anisotropic flux to discern this inner boundary of the IB or inner boundary of this curvature scattering driven precipitation using the MAXI dataset. So based on this criteria that validated against the alpha measurements, we are able to conduct a statistical study over a 5-year data set of MAXI and correlate. So that for each of the precipitation pattern, we'll be showing the distribution of this, distribution of each of the precipitation pattern in this MLT versus L-shell plane or domain. So first of all, for the waste-driven precipitation, we have identified more than 1,000 orbits in total over this 5-year data set. So although that you can see them all over the place in the entire MLT range, that you can sort of see that this predominantly occur in this MLT range of post-midnight to about noon sectors, as expected for waste-driven precipitation. And very interestingly, that these red dots marks those intervals or those orbits that shows simultaneous greater than 1 MeV electron precipitation during these waste-driven precipitation events. And similarly for the image wave-driven precipitation, we show the same distribution. And for this data set, we identified about 700 orbits for image-driven precipitation. And you can see that a predominant preference in the dusk sector as expected for image waves. And very interestingly, that these blue dots marks those about half of the orbit shows simultaneous sub-MeV electron precipitation as seen by MAXI at ISS. Potentially related, again, about the specific features of image waves scattering. And last but not least, this shows the same distribution for field line curvature-driven scattering in the same format. So we can see that surprisingly, we have quite a few orbits of this showing this IB signature or curvature scattering driven precipitation at such a low L-shell, below 4.5 RE. And from this distribution, we can see the most predominantly that this IB was observed on the night side, as expected again for this mechanism here. And interestingly, this red dots marks those, again, about half of the orbits that shows simultaneous correlate X channel response around the inner edge of this isotropic boundary. So that, in other words, this just means that curvature scattering, at least in half of these events, was able to extend to these rather relativistic energies in the outer radiation belt. So just to quickly summarize that we have been using this so-called calibrated data set from Carlick and Maxey to look at the occurrence rate of field line curvature-driven scattering at the outer radiation belt, low L shell. So we found out about 17% of this all SS orbit with precipitation have this isotropic boundary present. And this occurrence rate is actually quite high, comparable to the image-driven precipitation in the radiation belt, and only a factor 3 lower than those laser-driven precipitation. And of course, that this deep earthward penetration of the IB or curvature-driven scattering is likely due to the penetration of this current shaded during substorm intervals. So basically, the take-home message is that this curvature-driven scattering is not only a mechanism that can operate in the plasma sheet, but it can also significantly contribute to outer radiation belt dynamics. Okay, so that's it. Thank you.
Okay, thank you so much for the two very interesting talks. Questions? Comments?
I have a quick question for Shoja.
Yeah, sure.
Excellent talk. Thank you so much. Very interesting new observations from ISS. I have actually two questions. A very quick one, which is what is the lower energy range for Colette and Maxey?
They only have integral channels,
Oh,
so that
integral
is,
channels.
yeah, the low
Got it.
energy end is just greater than 300 keV. Yeah.
Okay, great. Thank you. And the second sort of question that I have, and that I think pertains to both Alphin and other data sets as well. I think that when you look at field line curvature scattering, you are searching for IB signatures, right? Which are indicative of strong pitch angle scattering.
Yeah.
And the question is that for when we kind of move inward of the plasma sheet into the radiation belts where the curvature is not nearly as high, the pitch angle scattering due to curvature may not be strong pitch angle scattering, but maybe a weaker pitch angle scattering that can mask itself to signatures that is more resemblant on something like wave particle interaction. And I was wondering if you ever looked for those signatures in the data.
You mean that whether this field line curvature scattering can contribute to radiation belt precipitation in a
Right,
more general case, right?
inside of the plasma sheet, and maybe not looking at the dispersion, but in the weaker signatures of weaker scattering.
Yeah, sure. That's a very interesting point. And let me bring up this what's the word? Observation from Alpha. Can you see this?
Yes.
Okay, so this is the dispersion that we're talking about corresponding to IB. And I suppose that you were talking about this lower L shell compared to this IB. So you can see that even at alpha, not even at both alpha and maxi data, actually the transition from this isotropic flux or this reddish region to this almost no precipitation, right, or this black region, or this very large deviation between these two channels are very sharp. So that's just give us the impression that this curvature scattering might not play as an important role inside of IB to the radiation belt dynamics. So that's why we focus on those isotropic region or this what's the word? Strong precipitation region corresponding to the IB.
Thank you. And we have other questions in the chat. Maybe Brian, would you like to speak up?
Sure, yeah. Hi, Jen. So it sounds like, I mean, by like 4 orders of magnitude or something, the dominant contributor to the NO production was the vibrational nitrogen. But did you look at what the dominant contributor to vibrational nitrogen production was?
Yeah, okay, so the production is caused by the enhanced temperature, not by the anomalous electron heating, aided by the enhanced plasma density due to the precipitation. So the contribution that comes from the two sides. The first enhanced temperature and enhanced density.
Okay, interesting. And for AEH, is it thermal electrons? I mean, are you just heating them thermally?
Yes, thermally,
Okay.
but it requires a high density to make it effect. Yeah, you understand that.
Yeah. Okay, thanks.
Any other questions? I have a very naive question for June. So is aurora continuum aurora?
Yes, it definitely aurora. It contains all the aurora, the standard aurora emission lines, and it's definitely aurora. I would classify it aurora.
So it's due to particle precipitation.
Yes, it must have precipitation and a fairly strong precipitation actually.
Okay. Okay, great. One last time, any questions? If not, let's thank our speaker. Thank you so much. And stay tuned for our next seminar. The announcement will be sent through SPA, where you can find them through our website.
Yes,
Thank you all.
we can announce right away that there will be a seminar in 2 weeks on low altitude auroral signatures. For details, please follow the web page. We'll advertise it shortly, and the announcements will be coming in the newsletter. And thank you all so much for dialing in and contributing to the discussion.
Thank you.
Bye.